Welcome to Maths All-Star. Many of you may have already participated this year's AMC8. I think its 25th problem is an excellent question because it involves many basic and typical techniques. Let's talk about it today. This problem reads like this. 1-inch squares are cut from the corners of this 5-inch square. What is the area in square inches of the largest square that can be fitted into the remaining space? Think about it before continuing. We are interested in these two questions. First, how to approach and solve this problem. Second, what related questions can we ask? Clearly, it is not too difficult to figure out the largest square that can be fitted into the remaining space should look like this, right? Typically, we need to know its side lengths in order to compute the area of a square. But in this case, do we really need to do so? What are the typical techniques we have discussed to compute areas in entry-level math competitions? As you may recall, many area calculation problems in AMC8 are done by cutting the to-be-calculated region into some smaller, easier-to-calculate ones, right? In this case, if you can think in this direction, you may find it natural to cut this square this way. The centerpiece is a just 3 by 3 square. Now the equation becomes how to compute the areas of these triangles. What is a typical technique to compute a triangle's area? It is its base multiplies height, right? In this case, the base is 3. And its height is 1. Therefore, its area is 1.5. Done. We really do not need to figure out the location of the inner square's vertex, don't we? Take a moment to review this problem and solution. What takeaway can you draw? We have mentioned many times, competition math is not about fancy formulas, but about applying basic techniques in a flexible way. All the required techniques to solve these problems are basic and well known. The real challenge is whether or not you can think of these basics and apply them during your test. Do you agree? I like this problem not just because it can be solved by a combination of basic techniques. I like it because it involves many important geometric concepts. So, is it possible to calculate its side lengths directly? The question is relevant because having the ability to solve a problem multiple ways is important and useful for any competition participant. Sometimes you may get stuck during the test and just cannot find the most beautiful solution. In such cases, it is essential if you can find an alternative way, right? Beautifully, it is possible to directly compute its side lengths. And this solution is also very typical, which I'm sure you have and will come across again and again. The hint is to utilize similar triangles and then apply the Pythagorean theorem. Both of them are two very important subjects in geometry, aren't they? I will leave this as your homework. The next question I'd like to ask is how many such squares are there? Essentially, this question is to locate the point A. Think about it. It turns out that the location of point A magically involves circle. We all know circle is one important shape in geometry. Even though this problem does not involve circle explicitly. A circle is implicitly involved if we want to determine the location of such point A. This is another reason I like this problem, because there is something beyond obvious for you to discover and learn. Obviously, in order to make the inner square as large as possible, its sides must touch the vertices of the 4 gray corner squares. If we connect the 2 neighboring vertices and make it as a diameter to draw a semicircle as shown, intersection points of the semicircle and the side of the 5-inch square give us the location of the vertices of the inner square. Can you tell why? Think about it. You will need to explain this in your homework today. Competition math is about a combination of basic knowledge and techniques. As we can see, this problem relates to many basics beautifully. This is why I like it a lot. I hope it can help you further understand what competition math is about too. That's all for discussing this problem. Thank you.